Now we have Julian to tell us about designing an energy system model from Syntef.
Yeah, hello everyone, and thanks that I'm able to talk about it. I don't have to present about Syntef. Truls did that fortunately already for me. But a bit about background. We wanted, or that's part of the project for the energy export from Norway, or decarbonized energy export from Norway. Quite a lot of energy system models so far come from either operations research, industrial economics area, or from the power system side. I'm a chemical engineer. For me, the approach is slightly different because chemical processes are slightly different than power processes, and to have that properly implemented. Now, to first talk a bit about the ratio for the development, if we take a look at the current energy system models, and here we have the high-level models like Times, Genesis Smart, we have a power system, we have extended power system models, and all of these ones are normally developed in a proprietary language. If you have looked into Times source code in GUMS, it's rather painful to try to understand what is happening. The same for Genesis Smart. And they are also quite difficult to extend with a slightly different technology description compared to what you have in the standard input-output process. One problem here is that the energy system, energy balances are normally not solved on the technology level, which implies that adding something or new technology descriptions for proper CO2 accounting, deactivation in batteries, and degradation in electrolysis is rather difficult. Furthermore, in these models, you have all regions which you want to model are treated in exactly the same way. You have parameters which then say, okay, we can't invest in a given region, offshore region, into, let's say, a nuclear power plant, but it's still quite heavily parameter driven. And we wanted to get away from that. And if you take, on the other hand, extended specialized models at NTNU in Norway, they work quite a lot with Empire for multi-stage stochastic optimization problems. And they normally focus on a single energy carrier. And if you then extend it, it's essentially in my opinion, most of the time, an unconscious bias. So essentially what you do then is you have a full model for, let's say, power, and you add to said power model hydrogen. You treat the different energy carriers differently. And that is not necessarily then leading to a good process. So our aim within that project is, when we realize we don't have any model which is able to solve that, what we want to solve, is that we want to have absolute flexibility with respect to time description, technology description, and investment modeling. The time structure part beforehand also originates partly out of that said project, and it's actually one of the applications where TimeStruct is used extensively. And all of these flexibility we want to achieve without any changes to the core structure of the model. So a person working with it has to a certain degree, understand what is happening in the core model, but does not have to change anything there. And that essentially leads then that we move away from a kind of parameter-driven flexibility where you say, you specify different parameters, which is also extensively existing, to a kind of type-based flexibility. Now, to give you a bit of an overview, Truls mentioned before, and that we are quite happy in Syntef to move away from monolithic models and instead have individual packages. The time structure package was one of the original packages which was developed here. And the time representation makes it, we took it out so we can reuse it for pretty much anything we want to have. Different models, be it for energy system modeling, be it for any other supply chain modeling. And we have one base model. And the base model is pretty much providing the framework of the system. These combination of these two models are normally, or is required for the overall framework. And the base model corresponds to an operational model, can be multi-time periods, but without any geographical features, without any major technology descriptions. It has a standard technologies representations in it, but it does not have anything specialized. And on top of that, we then can set a geography package, which allows for investment in transmission corridors, transmission modes, different description, whether it's pipeline transport, mixing of hydrogen and natural gas as an example, and also for investment modeling. And the last point, which at least for me as a chemical engineer is rather important to include, is specific packages for the individual energy carriers. And all of these ones here can be developed. We have a few ourselves. We're looking into mostly CO2 and hydrogen for us, but it also is possible to use whatever you want, develop something on top, and just reuse the base structure. And all of these, one is working through Dispatch, which most of you attending JuliaCon obviously have quite a lot of knowledge about. And another point which was rather important for us is that it's rather straightforward to understand how the model is built up. So the overall flow structure to understand what is called when, how you can reuse parts of the code which was developed beforehand, that all of these things are there and easy to follow. Now, that is the overall modeling structure. Let's go a bit more into, let's say, the technology descriptions and what we can do there. For those of you familiar with energy system modeling, you always have an energy source, energy sink, and energy node. For us, we implemented all of that with abstract types, which allows us to essentially then use that for the individual dispatch for the different functionalities for that. And if we want to have a specific technology, we use composite types, allows us then to have the parameters specifically for each technology. And similar to what was presented beforehand, we also use YAML files for providing the technology input there. For the overall point here, and now I have to zoom in a bit because I think that is rather small to see. It's essentially for us, we use a classical time structure point, but the key point is that for each new technology you want to have, you pretty much have to define 2 functions, and that's it. 2 functions and a type. And let's zoom out again. Quite a lot of these things can be also reused. Standard mass balance or flow in, flow out for an energy system is pretty much independent, or most of the time independent of a given node. So in that respect, we also have a further workflow for constraints functions, which allows us then to reduce the number of lines we require and focus instead of reusing what was done beforehand. And we implemented these functions for quite a lot of different key technologies. We have standard sources, sinks, conversion units, storage units, but we also use it for other technologies. That one here, to zoom in again, is just showing a bit how we can calculate the constraints functions, which are then here. For example, you don't see for the capacities something specified for network or for sources. Instead, it just uses the standard node. So the overall type hierarchy allows us to reduce then the structure. And the first time I'm actually using Zoom, so it's a bit of a mess. And we implemented that for quite a lot of different things. We had the capacity constraints. We have the variable OPEX or fixed OPEX constraints. So essentially, it allows us to also work on specific technologies. One key point which we have not yet implemented, but it's a part for the near future, is also for the stochastic versus deterministic analysis. Truls showed you the 2-level structures beforehand, where you can have several, let's say, representative periods, and that we can also pretty much then change on the level where it's required, where you have a constraint which is dependent on the previous time state. So essentially, you do not have to do any major changes if you want to implement that. Pretty much just the function changes. Quite a lot of these things could be also solved in Python PMA using object-oriented programming. But then again, you could have an explosion of possibilities and couplings, which is way simpler to do that within Julia. To give you a few examples, what we have implemented here for our project is for CO2 storage units, because most of the time CO2 storage is different in accounting of the total stored volume compared to other technologies, because you have the total limit. And if you say for the next 25 years, you have to have an upper bound which can be filled really fast early or really fast late. And that implementation of this technology takes 1 hour, and then writing 5 hours of tests that it's doing what you want. But we also have, coming from Norway, quite interest in hydropower modeling, how the hydropower flow is working to implement that properly, and for electrolyzer degradation, what leads to bilinear terms, and is a bit of a problem, but still solves. Now, talking here about the extensions, we only need, for writing a new package for this, we only need to have a dispatch on the node type. And as I mentioned beforehand, if you want to introduce a new technology description, be it a heat pump, where you have dependency on the outside temperature, or CO2 storage nodes, you pretty much only have to formulate a new composite type and 2 functions. So in that respect, moving away from the standard input-output efficiency approach in energy system modeling is rather simple in this situation. And so here is one example looking into a non-dispatchable renewable energy sources. What we do here is pretty much taking a look at these functions. The composite type, variables creation for the individual nodes, which we're currently doing for all non-dispatchable renewable energy sources in the same kind, plus the constraint functions for that. And that is pretty much all needed if you want to have a new technology descriptions. Nothing more has to be done. Similarly, you can also dispatch purely on the constraint function, which I have not shown here. So you don't even have to go too much into the overall system if you trust that the mass balances and so on are working in what we have done beforehand. You pretty much just write new capacity constraints. And lastly, none of that here requires any changes to the core structure. So to give you a bit of an example, it's what we are looking into. It's essentially a demand where you can either use, let's say, hydrogen or natural gas equivalently, although it has an impact on the CO2 emissions within this demand. To write that change was a small change in the constraint function, a new composite type. That actually took me only half an hour for that case study. And then, again, 2 or 3 hours of tests, and it was there. And when I was working with other models beforehand, you're always required to have to do some changes in the core structure to extend things. And we also have in the different composite types, which are describing the individual nodes or technology nodes, a wildcard data type, which we plan to use slightly more in the future. One thought process is here that we want to use it for LCA functionality for the individual technology nodes, or we use it as well for investments at the time being, but it allows something to put on top what is existing so far for new features. And then again, the type usage simplifies that we can use the proper function which we want to. And that is not really easily doable in other technologies. And as mentioned, can be separate functions, for example, for classical LCA analysis. Now, that is pretty much the approach, what we can do for different technology descriptions. It's most important, in my opinion, for things where the standard approach may fail. Let's say battery degradation, where it's, if you consider it or not, has an impact on how you operate it. Similar electrolyzer degradation, and these things can be fast implemented if you know what your model should imply. Currently, we're also implementing a direct air capture unit model, and it's rather straightforward and simple. Now, the second part, I want to talk about investment options. There will be most likely quite significant changes happening here. We were also, while we were here at the conference with our colleague Lars, Truls and I, we were in contact and thinking about the further development. But to give you the classical challenge for investment modeling is that in most of the models, you have a single investment option for all technologies. So either the model is based on discrete investments, or it's based on continuous investments. Some of them also have piecewise linear for economy of scale included, or learning curves, but it's most of the time it's an either or. You choose what you want to have. Now, you want to be able to have the possibility to change investment options for different technologies. For those of you familiar with these technologies, if you have a natural gas reforming with a CCS plant, they are normally in the range of 800 megawatts plus, because they have a significant economy of scale. So in that respect, it makes sense to have an integer investment, discrete investment for that technology. On the other hand, electrolyzers, excluding balance of plant, purely electrolyzer stacks, have way less economy of scale. It's essentially in this repetition. So if you reached 100 megawatt, they're pretty much multiples of 100 megawatt. Wind power, largest one, is currently in the range of 18 megawatts. So if you're talking about gigawatt installations, you can treat it as continuous. But on the other hand, you also want to have the same technology in each region, the possibility to change whether it's continuous, discrete, or how you want to model that. So let's say we have a smaller wind farm potential here. It makes quite a lot of sense to have it discrete. Well, if you're looking into Norway as a single node, why should you bother about these integer variables? And to give you a bit of an overview what type of investment options are generally existing, we have the continuous investments used in times and most of the really large-scale models, because otherwise you can't solve that. We have semi-continuous investments where you have a lower bound. We have fixed investments, which pretty much just say you have to invest in it or not in a fixed capacity, and the discrete investments, which I jumped over. And for us, we want to pretty much decide on the model creation part what type of technology should be utilized for that. And the investment package at the time being is an extension to the base package. It's going to be potentially also more independent like TimeStruct, so that the overall investment implementation is openly available for whatever model you want to utilize it. And key point here is, for the time being in the implementation, that we're looking into an energy model, which can be an operational model or an investment model. And that is, these types pretty much include all the global information which we have generally available. And again, so it's essentially, if we have an investment model, we overload the function from the base to pretty much just include the investment constraints on top of that and create the variables for the investments required only for the technologies which have investments. And that can be also, yeah, pretty much just an overloading small part on the model type, and that works neatly. And the similar approach which we have for the investment options in itself, using that based on type structure. And in that respect, we pretty much have we have a simple approach where we do not have to copy code from one point to the next point. We pretty much just reuse what is existing already beforehand and only change the parts of the model which require to change. And we have a similar approach as well for the lifetime of technologies, because most of the time, if we have a time structure which says we have 5 investment periods of 5 years each, total 25 years, and a technology has a lifetime of 18 years, it's a bit always a discussion. How should it be handled? When should it be retired? And that is also included different ways to see for the lifetime. So you can specify that for each technology in each individual region, however you want to do that. And now we are coming here at the point where Julia strives or is amazing for working with that, because with all the different technologies which we have and all the different lifetime approaches and investment options we have, we end up with the potential for, or have a huge potential of combinations of the individual technologies with different investment options, with different lifetime options, and even write new technologies. Now, how do we see it with a way forward? And as I mentioned before, and we have quite a few packages already developed. They are currently internal still. It's a bit of more difficult in this project to publish that, also due to industrial partners. And as Truls mentioned, it's impossible to reach anyone in Norway in July. So it is an issue, but we prepared it in a way that I hope we can have it open on GitHub in August. That is actually my biggest point. And we have geography I have not talked at all about, but we have also a geography package which allows for different areas, transmission corridors between set areas and transmission modes. So specifically, you can limit what is allowed in between. You can have then also, contrary to what is done in quite a lot of models, you don't have to look into the cost per kilometer, but you have the specified cost, differentiate onshore, offshore, all these things easily doable. And the interesting part is as well with the areas that you can add additional constraints on different type of areas. So saying that from a given area you can not export too much. That is in Norway a rather interesting discussion right now due to the energy crisis in Europe. And most of the approaches which we follow in geography are similar to the base package. So if you understand the base package, you understand how it's done in the geography package. And we have also quite a detailed description included within that project for non-dispatchable renewable energy sources, pumped hydropower or classical hydropower, electrolyzers with degradation and stack replacement, which complicates it quite a lot because it leads to bilinear terms which cannot be avoided, and also CO2 storage with proper accounting of the total storage volume. Now, when we look into the future, that model, or overall the development, comes from a project which started in initially 2019, coding started in 2020 on this part, but it's replacing other models which we currently have at SINTEF within energy systems, and also simplifies future development. And there are quite a lot of projects in the pipeline starting right now. And what we also want to include, or what I directly want to mention, is that we have this data type. Currently it's used for investment models, and it allows us for easy extension of the overall system. So essentially for each technology that you have the possibility to extend on the description of the node, that you can have LCA calculations included, depending on what type of data you provide. And it's not necessary that everything is provided to everything. You could choose based on the technology. And similarly, we want to have a few things like dependencies between investment options. You have to retire A before you can invest B, which is in the current framework takes a bit of time to think about how we can include that best. And also work a bit more on further flexibility for variables which we consider to be global for the system, like emissions and constraint calculation for these ones. And lastly, second lastly, as said beforehand, for broader user base, it's rather important to have it easy accessible. For me, to create a new case study goes really, really fast because I know the model and all the parts of it. For others, it can be a bit more difficult, but that is going to happen as well. And the most important part, actually, in my opinion, is release of the packages on GitHub. It will happen eventually, hopefully in August. We have that also signed with the Research Council of Norway that we have to release it. Otherwise, we would not have gotten the project. We started also working on it, but the holidays somehow put a break in it. And lastly, I would like to thank the project partner. It's quite a combination of different energy companies in Europe, and its overall development team consists, of 8 people, 7 people. It's depending. We get more and more people working on it, and the GitHub link so far points towards the project where we're going to upload everything. It already has a README. The only thing missing are still the packages. And actually, these are the most important things, but at least it's already there. And with that, I would like to thank you, and I'm happy to answer questions in the next 4 minutes.
Thanks very much. So we already have a question here. And I'll ask us to restate the question again for the room and for the camera, please.
Okay, the source and sink nodes model abstraction is brilliant. That has applications in a variety of sectors, including data and vehicle transport. Was that design inspired by one of those other sectors? And conversely, can this package be used to model transport of other things besides energy, like data and vehicles?
So the question was whether source and sink, which is a concept which is frequently used as well in other commodity transport models, and whether the package could be also used for outside energy. Personally speaking, I would say yes. We do not differentiate too much at the time being. We don't work with units yet. It's one of the many points on the list which we want to implement. But for us, for example, CO2 transport is a rather important point. Norway tries to build a business model around that. So the whole system could be used for CO2 transport network design, which then is less energy, or it's not energy, but it's mass. So I don't see any issue why it should not. We're rather agnostic at the time being, but we still have to improve on the units. That we essentially have a bit of a save there and don't require that anything is done a priori, but by the user that it works out.
Maybe one more question, or sure.
I'm not an expert on any of this stuff, but I've also seen packages from the U.S. National Renewable Energy Lab, Power Systems. Is there any relationship between Power Systems and the package you have here?
So the question was that there are also quite a lot of other packages for energy system modeling, from NREL, as we've seen before, and with power system analysis, and also natural gas package. No, we decided, or we used quite a lot of concepts which we developed in previous models used at SINTEF. But we decided to go from scratch and have the full control over and overview what is happening, and try to make it as simple to use as possible.
Can we all thank the speaker again for a nice talk?